Greetings. Good day. How are you guys doing today? Welcome to our chemistry lesson number 10. Today we're going to be looking at the concept of stoichiometry, specifically relative atomic mass. It's a brand new topic. If you are looking at your textbooks, it's effectively topic number 4. I skipped topic number 3 for now. We'll do materials when you guys come back to school. I didn't want to do that one online. I feel that it's a simple concept. Topic number 3. Not that it's very simple, but I just didn't want to do it effectively. I just didn't want to do it whilst we're doing these online lessons. I preferred to move to stoichiometry, not because that is difficult, even though there's a myth that stoichiometry is difficult. It's not. It's very simple. Right, so we are looking at relative atomic masses and our objectives. Let's just take a look at the objectives. By the end of this lesson, we should be able to define the term relative atomic mass of an element, to calculate the relative atomic masses of different elements, to define the term relative formula mass, and then to calculate the relative formula masses. Okay, so there's an error there. It's supposed to be relative formula masses. I will correct it before I send you this document. Right, so atomic masses. What are we talking about? If we recall, we looked at our periodic table. We've been using them throughout. And when you look at your periodic table, you will find that there are numbers that are there either on top of the symbol. If it's hydrogen, if it's chlorine, you'll find chlorine 35.5, oxygen 16, nitrogen 15, sodium 23. You'll find those mass numbers being on top, right? And we say that these mass numbers, they come about as an addition of the mass of the protons and neutrons, which are found in the nucleus of the respective atoms. But what's important to note is that these particles, they're extremely small. So when we say we have measured the mass of sodium, and we have came up with the mass of sodium as being 23, this is just 23 AMU, which is a special unit. It's a special unit that is designed for us to be able to measure the mass of extremely small particles. Because remember, we are talking about subatomic particles. They're extremely light. But even though they're extremely light, what was done was that there was the development of a scale on which these extremely light particles could be measured against. And that then brings us to the concept of relative atomic mass. And we have a relative atomic mass scale. This relative atomic mass scale is based on the carbon atom, which is defined as the standard atom on which all other masses are effectively being compared to. You see, when you say relative, to say is something heavy, is something light, in comparison, or how heavy or how light is something in comparison to one atomic mass of carbon. Let's say, let's bring it to, let's say maybe an abstract or maybe a more realistic level. I'm trying to think of an experiment or a practical situation. You see, if we say we don't have a scale, right? We don't have a scale at the school, but we want to know if how heavy the people are, right? We want to know how heavy, let's say, our bags are, or how heavy our books are. We will take maybe one book, let's say the chemistry textbook, and we will say, if anything has the same mass as this chemistry textbook, if the mass is exactly the same, then we will say its mass is 1. Right? So if we take at a book and then its mass, we feel that this book weighs twice as much as the chemistry textbook, and then we'll say its mass is 2. And then we say, this one weighs, we think like it's half of the mass of the chemistry textbook, then the mass of that one then is then half. We ascribe a certain mass to the textbook. If we say the textbook is 100 grams, if something weighs like it's double the mass of the textbook, then that thing is going to be 200 grams. If we say this book feels like it's half of the chemistry textbook, then that book is going to effectively have a mass of 50 grams. The mass of whatever we're measuring is in relation or is relative to a standard that we have set. And the standard atom that we use when we're talking about relative atomic mass is the carbon atom, which has a mass of carbon 12 atomic mass units, right? 12 atomic mass units. So a mass of one neutron or proton is equal to 1 atomic mass unit, right? So everything that is measured is basically going to be in relation to those mass units. So it says here, in general, 1 atomic mass unit is defined as a mass exactly equal to 1/12 of the mass of carbon 12. If your math is good, just pause the video for a minute and try to understand the statement, to say why would they say that. I hope you were able to just do a simple calculation which would show you that if the mass of a whole, let's not use abstract ideas anymore. Let's use carbon. The carbon atom has a mass of 12. The carbon atom has a mass of 12. And if we say that mass of 12 represents 12 atomic mass units, 12 AMU. So if something has a mass of 1, it means it's equal to 1/12. It's equal to 1/12 of the carbon atom. I hope that you guys are able to understand this, and you're not actually fitting in. In my mind, I'm thinking that it's going to be difficult for you to understand this, but probably it's actually very easy for you to understand it. So let me not belittle you or demean you and then end up thinking that you don't understand. I will work with the assumption that this concept is very simple for me as it is for you, or for you as it is for me, right? So this relative atomic mass, AR, okay, AR being the symbol for relative atomic mass, you'll find that for you to be able to calculate, we are given a formula here. Relative atomic mass of an element is defined as average mass of its isotopes compared with 1/12 of the mass of one carbon 12 atom. Right, so we're gonna bring in an issue of average mass of the isotopes of an element, which is key. I think if we were just going to go on the periodic table and pick numbers and say the mass of the mass of magnesium is 24? 24? Yeah, if you're just going to go there and you're going to pick it like that, then it will be pretty simple. But then you'll find that most of these elements have isotopes. They have isotopes. And because they have isotopes, whenever we're going to calculate their masses, we have to take an average mass of the isotopes of those elements. Let's look at the illustration that we have here. I'm going to play also a video where I hope that a different voice, just hearing it from a different voice, will be able to explain it, maybe in a way that's simpler to the way that I'm doing it. So if you look at chlorine, you remember we did a topic on isotopes when we talked about radioactivity. We talked about how different elements have different isotopes. The element chlorine actually has 2 isotopes, the isotope chlorine 35 and the isotope chlorine 37. So when you want to find the atomic number now, because when we say isotopes, we are talking about naturally occurring isotopes of chlorine in the environment, in nature. So if you were to go into nature, you will find that for every 100, this is just, what do you call it, a sample. If you were to take a sample of 100 chlorine atoms, you would find that most likely 75 of them would have a mass of 35, whereas the other 25 would have a mass of 37. So you can now use these percentages and abundance in nature, right, to calculate the average mass of chlorine. So what happens here is that let's look at this equation that is here. You then take the percentage abundance and you multiply it with the mass number of that isotope. So let's say here the isotope chlorine 35 multiplied by its abundance, 75 multiplied by 35. And you add it to the percentage abundance of the other isotope, which is 25%, multiplied by 37. And then you divide by 100. Then you divide by 100. Then you get this one. Let me just bring in the video and see if it's not better explained there.
Relative atomic mass of an element from its isotopic abundances. If we consider carbon, its relative atomic mass is very close to 12 atomic mass units. This is because, in nature, 99 atoms out of 100 atoms of a carbon sample are carbon-12 isotopes. Another way of saying this is that carbon-12 has a 99% isotopic abundance. However, not all relative atomic masses of elements are weighted in this way. Chlorine, for instance, exists as two isotopes, chlorine 35 and chlorine 37. How many protons and neutrons do you think each chlorine isotope has? Remember, the mass number for an isotope is equal to the number of protons it has plus the number of neutrons. Pause and select from one of the following options.
Okay, so you can check to say how many neutrons are there in chlorine 35 and how many neutrons are there in chlorine 37. If you go and you look at the mass number and the atomic number, you'll be able to determine for you to get, because observe the red number, that's the atomic number, that's the number of protons. The number of protons don't change, right? Remember that the number of protons don't change. So it should help you when choosing, because the number of protons don't change. So I'm sure it's a simple question. And just pick A, B, or C. Which one do you think it is?
Use the chemical symbols to help you work this out. Both chlorine 35 and chlorine 37 have 17 protons, but the chlorine 35 isotope has 18 neutrons, whereas the chlorine 37 isotope has 20 neutrons. The answer was A. Did you get it right? In nature, out of 100 atoms of chlorine sample, 75 of those atoms are chlorine 35 isotopes, and 25 of those atoms are chlorine 37 isotopes.
That right there is the concept of abundance. That is the concept of abundance, natural abundance, to say if you're in nature, if you could walk around picking chlorine atoms, you'll find that 75 of them are going to be chlorine 35, 75% of them. The other 25% will be chlorine 37. Okay, this is scientific fact. So it helps you in the calculations because you always have to use the percentage abundance multiplied by the nucleon number, right? So whenever you're going to calculate, you're always going to say percentage abundance multiplied by nucleon number plus percentage abundance multiplied by nucleon.
For you to be able to work out the relative atomic mass for chlorine, you have to multiply the mass number of the isotopes with its abundance, percentage, and add these products together. This gives the total mass number of the isotopes. Using this data, can you calculate the total mass of chlorine isotopes using their abundance and mass numbers? Pause, think, Choose and continue when you're ready.
Yeah, right now you're doing the calculation. Just do the calculation. Try and see which one would fit into the narrative we've given. Remember, we're saying percentage abundance multiplied by nucleon number plus, again, percentage abundance multiplied by nucleon number. So you must remember that chlorine 35 has a percentage abundance of 75%, whereas chlorine 37 has a percentage abundance of 25%. That information should be enough to help you choose to say is it A, B, or C. Right, so do your calculation, and if you pause, you can also pause this video and then come out with a proper response.
The answer is B. You have to multiply a 75% abundance in the chlorine 35 isotope by its mass number 35. You then have to multiply a 25% abundance in the chlorine isotope by its mass number 37. When added together, this gives a total of 3,550. The final step in calculating the relative atomic mass is to divide your answer by 100. This is because the abundances are given as percentages. This means chlorine has a relative atomic mass of 35.5.
35.5. So you should be able to carry out, these calculations. This is the example that we gave. It's the same example that I gave you guys in your notes, right? So when you do, please, you're going to do these calculations for determining the relative atomic masses of oxygen, carbon, and hydrogen based on the information that is given there. Well, I don't know why I wrote lesson 3 there. That's supposed to be isotope 3. I'll again correct it. It's not lesson 3, it's isotope 3. Then if we now know how to calculate relative atomic masses, then we just move on to so it's an extremely simple concept. The relative formula mass now would come from a relative formula mass or relative molecular mass. Relative molecular mass is now saying we have water. Let's say we have water. Water, what are the atoms that you find in water? Water is H2O. So if you have water, you now want to find the relative atomic mass of hydrogen, relative atomic mass of oxygen, and if you are given those relative atomic masses, you are now able to calculate the relative molecular mass of the whole molecule. Because if you can find the mass of the individual atoms, it means you can calculate the mass of the molecule, right? So I gave you here an example using the sodium chloride molecule, right? Sodium chloride, a combination of sodium and chlorine. So you have the relative atomic mass of sodium given here. That's the relative atomic mass of sodium. Here you have the relative atomic mass of chlorine. And if you add the two, it's just an addition, right? But what is key is understanding the formula of the molecule that you have been given, right? So if we say, let's say lithium oxide, you're not just going to take lithium and say lithium plus oxygen as if. You have to remember that the formula of lithium oxide is Li2O, right? It means that there are 2 lithium atoms that are going to be there in that molecule of lithium oxide. So the molecular formula, right, is important in helping you to calculate the molecular mass or relative molecular mass. All of this is relative. All of this is relative to what? Relative to the mass of a single carbon atom, which is a mass of 12. So here again, using the information that is given in this table, you can then calculate the masses of those compounds that are given there, or those molecules that are given there. What is key is just to know their respective formulas. So it's a simple concept. I think you'll find that most of the concepts that we do are not difficult. All that is required is just a bit of give. You have to give your attention to it. Otherwise, if you just want to wake up and guess molecular masses, you're just gonna faint, or you're just not going to get any of it. And then you end up saying, no, I can't understand chemistry, Chemistry has no grudges against you. Nor does physics. It doesn't even know you, so it can't hate you, right? But what is required is a certain amount of effort, a certain amount of attention and patience. So thank you guys for watching this video, and carrying out the calculations. It's in the exercise, it's in the practice. The practice is what is key. Okay, so I will see you guys in the lesson. Thank you very much again. This is Marshall A.C. Candiado.